Hello, welcome back. In this segment, I want to talk about an interesting problem related to multiple threads. Let us consider this basic class called counter, which has a variable n, and we have a method for incrementing it, decrementing it, resetting it, and we can get the current value. So we can also visualize it as follows, right? You have a class called counter. Let's create an object called counter, right? What is inside the counter is just variable n. At the beginning, it is 0. And then we change the state by either incrementing it or decrementing it or resetting it and so forth. So that's basically what this counter is. And if you go down further, we have separate threads for all of those operations. One thread for incrementing the value. As you can see here, there's an inc thread which takes the counter object, a run method which runs indefinitely, right? Because I have a while true, and then it checks whether the current value of counter is bounded by some upper bound. Upper bound is an input to the constructor. If it is, it keeps incrementing. Okay. Similarly, if you go down further, there's a decrement thread, which also takes the counter object, lower bound. And in contrast to the increment, the decrement operator uses lower bound. If the current value is greater than lower bound, that means we can keep going down. That is the reason why we are calling the decrement here. It's also running an infinite loop, right? And then we have the reset thread, which checks whether the current value of the counter reaches the upper bound. If it is, it resets it, okay, to 0. That's basically the reset method. So the are 3 threads so far. And I wanted to have another thread called invariant thread to check a property. What property I want to check is that at any moment, the counter value is bounded by a lower bound and an upper bound. That's basically what the invariant thread is going to check. It's also an infinite loop. It continuously checks whether lower bound is less than or equal to the counter value and the counter value is less than or equal to upper bound. Okay, counter is only the object we create in the main class here. There's a test driver, for example. We create a counter object. We have the lower bound and upper bound defined here, like 0 and 1, just for demo purpose. And we have increment thread, decrement thread, reset thread, and invariant thread. All the threads are created here, and we start running them. Okay, so now the question is, can we check the assertion, right? The assertion is lower bound is bounded by counter value, and the counter value is bounded by the upper bound. How do we check this? We can compile and run it and see whether the Java runtime can detect this problem. Let us do that. But before that, let's visualize the scenario. So you have counter being defined with n equal to 0 at the beginning. So we have multiple threads. Let's say we have the thread for incrementing n is called inc thread, okay, which is going to operate on this state variable n. Inc thread is going to increment the counter, right? N++ eventually. And decrement thread, on the other hand, is going to do decrement naturally. And okay, and then we have the reset thread, which is basically setting the n value to 0. So there's a third thread for reset. So these are all the 3 threads that are changing the state of n. The 4th thread is more of an invariant thread that's checking whether at any moment, right, your lower bound, let's use the notation LB, right, is less than or equal to n, which is less than or equal to upper bound. Okay, so it's not going to change the state of n, but it's going to read it. So I'm going to put an arrow mark opposite direction to just show it's a read. And this arrow mark, well, let's use a different notation. Let's fill the triangle to show it's right, and unfilled triangle means read. Okay, anyway, so the read thread is the invariant thread. The rest are all state changing threads. The question we wanted to ask is, for this design, does this invariant hold true that lower bound is less than or equal to n, less than or equal to upper bound? Okay, how do we check this? So let me get out of this editor and compile and run it and see whether we can have Java direct this thing for us, right? Java C race test.java. So it is compiling. Since I have assertions in the Java code, I need to use -EA to enable the assertions, right? And now I'm just checking whether the race condition is detected, meaning is there a violation of the invariant? Let us check whether we can detect that first. Okay, so far it's not. So it has been running for a while now, and so far the race condition is not detected. If there is any race condition, it's not detected. So I'm going to use an interesting technique in the computer science world. It's called model checking to see whether we can detect the violation of the race condition. Let us put together a design based on this diagram. So I'll have three threads: sync thread, reset thread, decrement thread, that operates directly on the variable n instead of using the abstraction counter, right? Counter is in Java abstraction. We are going to just get rid of that and directly operate on n in that model. And then we will have another thread called invariant thread that checks whether lower bound is bounded by n, bounded by upper bound. Okay, so let us get into the design of that. I've already designed this in a model checking language, and I will show you that now. Okay, so here is the model of this thing. The syntax of this may be a little bit weird if you are new to this. Let me briefly explain it. This is a language used by the Spin model checker. Spin is a model checker developed approximately 30 to 40 years at the time of this recording. Anyway, it uses a language called Promila, which is a specification modeling language. So the constructs are not that foreign. We can hopefully understand it easily. So we have a active means, it's a thread that can start running right away. That's the meaning of active. A process type means you're specifying a procedure. You can imagine like that, or a process. A process, yeah, is a better word. Inc is the name of the process, if you will. And here is your infinite loop of keep on checking whether n is bounded by upper bound. If it is less than upper bound, we can keep incrementing n, right? That is the meaning of this syntax. Similarly, if n is greater than lower bound, then means we can keep going down. Okay, and that is what this is doing. And reset is essentially, if n hits the upper bound, we set the n to be 0. And here is your invariant, right? That the lower bound is less than or equal to n, less than or equal to the upper bound. That is the invariant, this thing, right? This is what we have coded here. Okay, so we have all of these 4 threads that we have modeled it very quickly using Promila, right? And then we can now see whether Promila can find, a spin model checker can find a violation of this invariant. Okay, I have defined, for the sake of a demo, lower bound to be 0, upper bound to be 1. Nevertheless, I want to see whether the invariant that I have specified here can be violated. Okay, so how am I going to do that? I'm going to use this model checker, right, to run this thing. So let me see, still the Java version is running. So far, no luck. It is not able to detect the violation if there is any. So let's see whether we have any luck with the spin model checker. Yeah. So we need to first compile this model using spin model checking tool. So I'm going to use the Spin 651 version, which you can download, by the way, from the internet. There is a Spin model checker available on GitHub. Okay, so I'm using this to first analyze the model called race.pml. That's the model that I put together. PML is the abbreviation for the Pramila language that I talked about. And yeah, Pramila modeling language. Now it generates a file called pan. If you see, there's a file called pan.c, which is just generated at the time of recording. And we can now compile this generated file, right, which is C code, by the way, and then we run it and see whether anything can be said about this model regarding that invariant. Okay, now I will scroll up a little bit to show you that there are some nitty-gritty details about state space, hash maps, and so forth. They may not be of immediate interest at this point, so I will skip those. But interestingly, it said it found a violation of the assertion. Okay, don't worry about things like depth. It's basically doing some search on a graph of state space it built. but it generated a file called race.pml.trial. We will analyze this file and look at the details. So what I'm going to do now is I'll use the spin model checker again to analyze this file. But there is a little bit of syntax thing, like if you run it with -p -t option, it's going to analyze the trial file. The T stands for the trial file, and don't worry about the P at this point. And you still give the original PML file as the input, and it will generate a trace, and that trace will tell you exactly where the violation happened, or at least one possible run that could lead to a violation of the invariant. Okay, so the trace itself is lengthy, right? The 32 steps shown here to show you the scenario where all these 4 threads working together, where the invariant thread found a violation. Okay, so let me, instead of walking through all the 32 steps or so, I will quickly show you some important places because I've already analyzed it manually. This is one problem though. Spin will generate a large output usually, and you have to understand, okay, which interleaving means, thread 1 ran first statement, thread 2 ran second statement, so forth. That lead to the violation. You have to do some homework to sort of get that exact sequence, but it's interesting because you get a concrete example to show you something's wrong. And let us now think through this step by step. Yeah, I will just move this thing somewhere else. So if you look at the trial, right, it said it found n equal to -1, but the invariant itself is saying that the value of n is between 0 and 1, inclusive of both lower bound and upper bound, right? 0 less than or equal to n, less than or equal to upper bound. But somehow this assertion is violated. Okay, why? We can look backwards. For some reason, n became -1. That's what the invariant violation is saying. So the last thing that ran is the dec. Dec is the decrement thread. Yeah. By the way, Pramila assigned a number 1 to that thread. That's the reason why you see proc 1 for the decrement thread. And we have only one decrement thread. You can have multiple decrement threads if you want, but we have only one thread. That's why it's putting a 1 here. Okay, anyway. So somewhere before the violation happened, the dec function, the dec thread ran, and let us look at what is the reason why this thing happened. Okay, if you look backwards a little bit, you see here before the invariant thread ran, the dec thread ran, and it detected the value of n. That's right, n equal to n -1. And if you now go a little bit up, at some point, you see here n became 0 at some point. Because we ran the statement n equal to 0 as part of the reset thread. Okay, so now comes the interesting question. So n becomes 0 at that 26th step. How come n became -1? Well, decrement thread ran and it reduced it. But then if you think about it, decrement thread is not supposed to decrement anything below 0. Okay, so what could have happened? Now, if you go upwards a little bit, you see here, there is a check for decrement, right? We are checking whether is n is greater than 0. Only if n is greater than 0, right? So here is the dec here, and here is another dec. But in the middle, the reset ran because what would have happened? Because n became 1 over here, somewhere up, the increment thread might have made the n to be 1. Maybe perhaps over here, n was 1. So when decrement thread ran, n is 1 greater than 0 is true, but it has not finished the n equal to n -1 step yet. In the meantime, the reset thread ran, and it set the state of n to be 0 over here. And then the decrement thread ran. Already the condition n greater than 0 is checked by the decrement thread, so it wouldn't go ahead and check it again, of course. So yeah, the next statement is n equal to n -1. That at that moment, n became -1, and that's why the invariant is violated. Okay, so let's see whether we have any luck with the Java assertion test. No luck. It's still running in an infinite loop. We have not detected a violation of the threads. As you can see, if you have multiple threads and if you use Java runtime enable assertion, it may or may not detect that. In this case, so far it has not detected. And none of the interleavings at runtime is able to detect the problem. Okay. So my main message is that if you know a design, like the design I put together over here, with 4 threads and the state variable, and you can fairly easily model that and generate a counterexample to validate your assertions. Yeah. So you can model check using multiple model checkers. I have used Spin Model Checker, which is one of the well-established model checkers. And of course, it's not directly model checking the Java code. There are some existing research like Pathfinder and so forth that you may be able to apply. But in the interest of time, I decided to just quickly model in Promila and show the interleaving that has caused the problem. Okay, that's all. Thank you very much for your attention.